All right, let's get started. So we are doing network flow applications, right? The main thing to remember about network flows is, in addition to sort of inherent interest, are the applications. So that's one reason you should care about network flow, and it's also, I guess, the classical example of combinatorial optimization. So for two reasons, it's very important. And let's recap again, what properties of network flow we need, because when you want to apply network flow, you need to know the properties that network flows satisfy, right? One, what are important properties of network flow, right? So let's think first, given a graph, a network, and SNT, we can actually compute network flow in polynomial time, right? So we know that we can solve it efficiently. The second thing is a very important property is the maximum min cut theorem, right? The maximum flow is equal to the minimum cut, right? And we also know that if the capacities are integer, then there exists an integer value network flow, right? If the capacities are integer, then there exists a maximum flow which is integer value, okay? And the fourth thing is that if I give you a flow, then I can decompose it into paths and cycles efficiently, right? Yeah? And if the flow is integer valued, the decomposition also will have integer valued decomposition. Okay, that's also important, okay? Yeah? So those are the things that you need to kind of remember, all right? In the sense that, if you want to use network flow, then you have to know all these nice properties, right? Both the maximum min cut theorem and the integrality of flow are very important in applications, right? Okay, and then we started doing some applications, and the most basic application is finding the maximum number of edge-disjoint paths between two nodes in a graph, right? So that's more or less, if you think about it, really it is saying, how many paths are there where, you put a capacity of 1 on each edge, right? So it's effectively integer flow. Okay, right? Because each path corresponds to 1 unit of flow going on that path, and if the capacities are 1, that means that they have to be edge disjoint, right? So in some sense, it is the most basic case of flow, right? Most basic case of integral flow, right? From all the properties we know, this is easy to compute because you just compute a maximum flow and decompose it into paths, okay? So now you have to, if you don't see it that way, you have to kind of walk through the proof a little bit more carefully, right? But once you get used to it, the fact that the edge disjoint paths are basically flow is immediate, basically, right? Because that's really, the most basic version of flow, right? All edges have unit capacity and we want integer flow, okay? Right? So, okay. So finding a maximum edge disjoint paths in a directed graph between S and T is the same as finding an integer flow, and we know how to compute that, right? Because capacities are 1 and then you decompose it, okay? Right? So, okay. So, till you get used to it, you have to make sure that you understand when you reduce something, you need to kind of go through both directions, right? And we went through it last time, so I won't repeat it. A little bit more tricky part of the reduction is that, and that's Menger's theorem. Actually, Menger proved also this maximum min cut theorem for unit capacities, right? But in some sense, if you take capacities and duplicate each capacity, suppose I have an edge of capacity 100, I can make 100 edges of capacity 1, right? And then Menger's theorem would imply maximum min cut theorem for integer capacities. Okay, so really, it is Menger already proved some things. He didn't give an algorithm though, and so that's why we credit maximum min cut to Ford and Fulkerson. Okay. Okay, now what about edge disjoint paths in undirected graphs? That's a little bit more tricky, right? Because flow we define in directed graphs, otherwise it's hard to think about incoming flow and outgoing flow, okay? Okay, but what you can show easily is that if you take a bidirected, if you take an undirected graph and take each edge and create 2 edges in this fashion and put the same capacity, then max flow in that graph, remember one more property of max flow is that if I give you a maximum flow in a graph, you can assume that you don't need cycles in that flow, Why is that? Because you can get rid of all the cycles and it won't change the value of the flow, right? Okay. So in some sense, by doing this and computing a maximum flow, I will eventually get a maximum flow where I'm guaranteed that there are no cycles in that, right? Okay, I can guarantee. In that case, I know that only one of the edges of this will be used, right? Okay. So if only one direction is used, then the reduction is okay, right? If you are worried that, we'll have a flow which uses both directions, but we know that there exists a maximum flow only in which the flow is acyclic, which means only one direction will be used. Okay? So in that sense, you can reduce the undirected graph maximum flow problem in the way you want to think about it to a directed graph problem. Okay? So you can compute the maximum number of edge disjoint paths even in an undirected graph using flow in the corresponding directed graph. Okay? All right? Okay. So Menger's theorem is also known for undirected graphs and that is edge disjoint paths. Okay? So okay. The more valuable and important thing that is a little bit more tricky is the node disjoint paths. Okay, here is a graph. First, let's think of a graph like this, right? I'm just making up a graph, Okay, how many edge disjoint paths are there between S and T in this graph? 3 edge disjoint paths, right? It's easy to see. But there are some applications where I want node disjoint paths. That means, I don't want, okay, no, the word node, the word node disjoint paths should be more formally said as I want internally node disjoint paths, in the sense that if I want ST paths, clearly S and T have to be in all of those paths, right? So when I say internally node disjoint paths is a proper term, right? Which means that the paths should not share any vertices other than S and T. Okay? So in this case, there is only one node disjoint path, right, between S and T, because all of them have to go through this middle vertex. Right? Yeah? Agreed? Okay. So how do we compute the maximum number of node disjoint paths in a directed graph? Okay. So this corresponds to finding basically what are called node capacitated flows. Okay? I put an extra problem in your homework, which probably many of you didn't notice. But so in general, when we define flow, right? When we define flow, we put capacities on the edges of a graph, right? Okay, why can't we put capacity on the nodes of a graph as well, right? What does it mean that I put a capacity on the node of a graph? It means I want the total flow going through that node to be no more than that number. Okay? Remember, the incoming flow is equal to the outgoing flow in each node, right? I don't want the incoming flow to be, which is the same as outgoing flow, to be more than some 100, say, some number I give you, right? How can we, that's also interesting, right? Maybe, you want to model a situation where you say, okay, I don't want, why am I putting, I have, you think of a road network, you want, each road has some kind of capacity, traffic capacity, right? But junctions also may have capacity, right? You don't, I may have a lot of roads coming into a junction. The junction could become a bottleneck, not the roads themselves coming into the junction, right? The junction itself has a capacity to route. Same thing with when you're modeling telecommunication networks, right? You can have, how do networks work, right? Every place, basically, there are links, right, connecting, which are like wires connecting our computers and stuff like that. But how does actually routing work, right? That means, I send a packet from here to somewhere else. The packet goes on a link, but at some point they have to be switched, right? There are always switching places, right? There are routers sitting in all, or in fact, most of the cost of the equipment is the routers, not the wires, right? What do the routers do? They have to kind of direct the traffic, right? But the routing, the speed of the router is actually a bottleneck many times. The switching capacity of the router is a bottleneck rather than the capacity of the wires. The wires are pretty easy, right? They can carry a lot of traffic, right? If you make the wires thicker, they can carry more capacity. But the switching capacity, the speed of the switching capacity of the router usually becomes a bottleneck, That's where Cisco and companies like that make a lot of money, right? They make these big fat routers which can switch at a very high speed because the packets are coming at a very high speed. Okay? But then the bottleneck there is also the node, not really the edge, right? Okay, so there are many situations where you want to model node capacities in addition to the edge capacities, or okay. So how do you model node capacities? The reason it's very easy when you have a directed graph. Okay, and here is how you do it. Okay, and this is a standard trick which is important even in shortest paths. For example, if I tell you that my length of the path depends also on the nodes, how do you model that just using edge paths, edge capacities or edge lengths, right? In directed graphs, you can easily do it, not in undirected graphs, and here is how we do it, right? Which is a standard trick. So suppose, sorry, what did I do? Okay, that was not... Okay. Okay. So here is how you do it, right? Suppose, they can have more edges. You basically take this vertex and split it into two vertices. Okay. It becomes V minus and V plus. Okay. And then you put an arc between them, and you put the capacity of the vertex here. Okay. And then you connect all the incoming edges here and all the outgoing edges here. Okay? All right, now you have to do it for all vertices. I'm just doing it locally for one vertex. Okay? So we basically, you would split every vertex into two vertices, in and out, V minus and V plus, right? And add an edge between them. Okay? So clearly from this, anything which comes here has to go through this arc, right? That's the only way to go. So all the incoming stuff has to traverse this and then go out, right? So by putting a capacity here, we are modeling the fact that you cannot send more flow or more, right? Okay, so you do it for everything. That means that, if U and V is an edge, then you connect U plus to V minus basically, right? Okay, so if you do this, you can model node capacities, okay, all right? So that's why we don't have to worry about node capacities in the sense that, edge capacities in directed graphs are enough. Okay? Well, this is a very important trick. You will see. Okay. Okay. So, and so you can do this. So now, if you want to, so finding node disjoint paths in a directed graph is the same as saying, okay, look, I'm going to put a capacity of 1 on the nodes now instead of putting 1 on the edges. Okay. Okay. But this reduction allows you to convert a node capacitated problem into an edge capacitated problem. Okay. All right. Okay. But then if you do that, but see, this transformation also shows that the capacities are preserved, right? In the sense that if the node capacities are integer valued, then the corresponding graph has integer capacities. Okay. Okay. So now if you want to go back to this example, you can convert, see, the capacities are what? The nodes have capacity, right? When you want to find node disjoint paths, the capacities are on the nodes and not on the edges, right? So you convert that graph into an edge capacitated graph where only these guys have 1 and the rest have infinity basically, right? Or big capacity, doesn't matter, right? You can even put 1 capacity, it doesn't matter, because if the nodes have 1 capacity, then incoming edges can also have 1 capacity, it doesn't matter, okay? Now you have to convince yourself that if you solve the edge disjoint path problem in that graph, then you are modeling node capacities. So basically you will get node disjoint paths once you come back from that. Okay. So what happens is that in this graph, when we convert, all the flow has to go through the V plus and V minus of this thing, right? So only one path can go through that. It becomes a bottleneck, right? In the resulting edge capacitated graph. So we'll correctly find out. Okay. So you can solve the node disjoint path problem in a directed graph by converting it into an edge disjoint path problem with this transformation. Okay, and then you can find node disjoint paths as well. Okay. Okay, the little bit more tricky part is you can do it even in undirected graphs. Okay, that is, you want to compute node disjoint. This transformation makes sense only in the edge capacitated graph. Okay, so if you want to do it in a node capacitated undirected graph, you have to do some more work. First, you bidirect each edge, right, and then you do this transformation. Okay, you have to do it in 2 steps. Okay, you start with an undirected graph, which is node capacitated. Okay, you first convert it into a directed graph where you put 2 edges for each undirected edge. So far, we're still a directed graph. Now you have converted from the undirected graph to a directed graph. And now you take the directed graph with node capacities and then convert it using this. Okay, you have to convince yourself that it will work. Okay, all right? And so you can compute the maximum number of node disjoint paths in an undirected graph between S and T efficiently. Okay, all right? Okay, and that also gives us Menger's theorem, which is that if suppose you have an undirected graph, the minimum number of nodes in V minus ST whose removal disconnects S from T is equal to the maximum number of internally node disjoint paths between S and T. If you apply the Maxwell-Minkart theorem after all the transformation, it says, if I have, how many node disjoint paths are there between S and T? Well, it is a minimum number of nodes whose removal disconnects S from T. Okay, that's the Maxwell-Minkart theorem when you specialize it to node disjoint paths. Okay, all right. It is also very important. You will see one example in your homework, 7, on why it's a powerful theorem. Okay. Any questions? Okay. All right. So you need to remember all these tricks. You are building on each other, and okay. So the graphs are very powerful, right? And once with reductions, you can do lots of things. So that's disjoint paths. Disjoint paths have many applications, but let's see something else you can do as well, right? You can have multiple sources and sinks. So you have to be a little careful because there are 2 versions, and this is the easier version, right? It's called multiple source and sinks. So maybe you don't have one source and one sink, right? You have many sources and many sinks, right? So in this graph, there are 3 sources and 2 sinks, S1, S2, S3, and T1, T1, T2. And you want to somehow capture the notion that you want to send stuff from the sources to the sinks. Okay? Maybe think of these sources as producers of something, right? Like oil fields or something, right? Or and the sinks are where the oil refineries are, right? You want to send the oil from where it is produced in the fields, some oil fields, to where the refineries are. And the network is, say, the road transportation network or shipping lanes or whatever it is, right? Okay. So the important thing is that it's all oil, okay, as opposed to oil and water or something, right? That you don't care which oil goes to which refinery, right? So you're really interested only in sending oil to refineries, right? Okay. In that sense, it's only what is called one commodity, right? That you're not distinguishing oil. It's not like, I want to send oil from this guy to that guy and water from this guy to that guy, right? Okay, when you're sending packets, we don't want to mix our packets, right? That's different. But here it's all oil, right? Okay, that's why it's a little easier problem than okay? But we do have multiple producers and multiple consumers of some company, right? We don't care which one goes to which. Okay, so what would be the notion of maximum flow here? We want to say, how much flow can we send from these green guys to the red guys? How much oil can we send from the oil fields to the refineries, given that our network could be a bottleneck, right? That we are not making here. We have infinite supply in the oil fields and infinite refinery capacity, right? That's what it means. And we want to know how much can we ship through the network, right? That's the maximum flow problem. So can we solve this problem using our standard network flow problem? Okay. I now have multiple green guys, multiple red guys, right? But you know, yeah, so maybe, you know, first thing to understand is what does it mean that, what is the formal definition of maximum flow when I have multiple sources and sinks? What would be a natural definition? How do we define when we have this scale? I mean, intuitively we see it, right? We want to ship as much from these guys to the other guys, right? So how do we formalize that? How, you know, mathematically, how?
A flow where you have multiple nodes which don't have the same output.
Exactly, right? You know, we normally, when we think of why is the source special in flow conservation, we don't have flow conservation in the source, right? It is generating flow, right? Okay, so basically, you know, here is the formal definition, right? You know, the flow should satisfy the capacity constraint. If it is not a source or the sink, we should have flow conservation, right? That makes sense, right? But if the source or the sink, we don't have flow conservation. But what is the value of the flow we are going to send? It is the sum over all the sources, what we think of as the value of the flow, right? How much flow is going out of the source minus what is coming in, right? If you had only one source, this is what we would think of it, right? If you have multiple sources, this is what we want. Okay? Right? So it's well defined. Now the question is, you know, can we solve this problem? Okay? Ideas. Yeah? Yeah, that's a standard trick, you know. We just basically create a big source, a big sink, okay, and connect S to S1, S to S3, and T1, T2 to T. And how much capacity should we put on this? Sorry? Sorry? I can't hear you guys. I'm not. Sum of the outgoing at each source. Okay, that's one possibility. What else can we? Conceptually, how much should we put? Conceptually, it should be infinity, right? We don't really want to limit how much source. Really, you know, when you think of S and T, we're not limiting it ourselves. It's just the capacity of the network, right? So conceptually, we should put infinity, right? Okay. Okay, but you know, infinity is good, except we can't put it in the computer, right? You know. So we can just put, as he said, you know, the sum of the, how much flow can we send out of S, all the sources? It is no more than, infinity is simulated by the total sum of the capacities of the edges, for example, right? You can't send more flow than that, right? So that's one possibility of putting infinity for infinity, or you can put a slightly better bound, which is the bound of sum of the capacities of all the source, outgoing edges of all the sources is a tighter bound than the sum of all the edge capacities in the network, right? You can even technically put a min-cut bound, basically, right? Whatever the min-cut is, right? If you believe that, so that's it, okay? Now you have to verify it to yourself. It's intuitively clear that it's doing the right thing, right? Yeah? Do you see that this is a reasonable thing to do? Yeah? Okay? Now you compute a max flow between S and T and you'll get the right answer, okay? So this is the power of directed graphs, yeah? Yeah, so that I'm coming to that next. Yeah, okay. So in this case, you know, we didn't have any limits, right, on how much S can produce, right? Okay, so next variation is supplies and demands, right? So let's think of the case where, you know, these oil supplies are actually not infinity but limited, okay? That means, okay, so what do we have now? In addition to these sources and sinks, this guy is saying I can produce 10 units, okay? This guy is saying I can produce only 5 units. This guy is saying I can produce 3 units. This guy wants 8 units. This guy wants 2 units, right? Right? Now the question would be, can we actually, now here we don't want to maximize the flow. We want to know, can we satisfy the demands? Okay? Can we ship enough from the sources to the sinks so that each sink is happy, right? We're not trying to maximize how much we're sending, right? This guy doesn't want more than 2, right? You know, in the previous version, maybe, you know, we would send everything to the sink, this guy, and nothing to that guy, right? That may be okay because we're maximizing the total we can send, but maybe it's not okay for this application, right? This guy wants 2, the other guy wants only 8. Okay? Okay. First, if the sum of these numbers is less than that, clearly we can't send, right? Okay? That makes sense, right? So now we shall assume that at least the sum of this green is more than the sum of the demands. Now the question is, can we actually send this much oil from these guys to these guys so that, if we don't exceed how much this can supply, and we get at least the 2 for this guy and 10 for this guy, right? What would we do? I mean, it's the same thing. We do the same thing, but except now we say, we have to put 10 here, we have to put 5 here, we have to put 3 here, because we don't allow this guy to send more than 10, right? Okay. Now we put 2 here and 8 here, and then, okay, now what should we do? How do we know that we will actually get the right flow? We did the thing, but we have to do something more after that, right? We create this network, which seems intuitive. What will tell us whether we can do it or not? Yeah?
If the max flow is at least 10, then you know that's...
You're right? The max flow has to be exactly 10, in which case we know that the only way we can achieve max flow of 10 is if this guy gets 2 and this guy gets 8. Okay? So when you do reductions, many of you sort of stop and say, we're done, right? But you have to say something more, right? You have to think through it also. We do this reduction, then we compute a maximum flow, and if the maximum flow is 10, then we know the answer is yes. And otherwise, we say the answer is no. Okay? So it's important to go through all the steps, right? It's not enough to say compute max flow. Then what? Right? Because it's a decision problem, right? Here we're asking, can you send flow through this network so that each demand gets its right amount, each sink gets its right demand value, and each source is not sending more its supply value. So you say, okay, do this construct this graph, compute a maximum flow, check that the maximum flow is equal to the sum of the demands, right? Then you know it's feasible. Okay? So this is the power of directed graphs. You can add things and nicely and get yeah. There cannot be flow of value 11 because this is a cut of value 10, no? How can you send more than 10 units from S to T in this network? Because this is a cut of value 10. If you remove these edges, you cannot send more than 10 units from, you disconnect S from T, right? So you can't send more than 10. Okay. See, the problem is, suppose you put 2 and, you don't put a bound on this. You can send maybe 11 units, but all of this may be going through this guy to T. In which case, you can't tell whether we can get anything to this guy. Okay. By forcing this guy to be 2 and 8 and asking for 10, there's only one way of doing that, right? 2 units come there and 8 units come there, which means if 2 units coming from there, this guy is getting 2. Okay? Yeah? That's important. All right. Okay. Okay, so those are nice applications, right? Now we're going to do a very important application, fundamental application with huge number of practical applications as well, which is matching. Matchings in graphs are all over the place, okay? Because they capture something very simple about resource allocation, which is, maybe it's because of the way human beings allocate resources or things. It comes up very frequently, right? Okay, but let's start with a matching problem in a general graph. So if I give you an undirected graph, right? What is a matching? A matching is a set of edges in the graph so that they don't share any vertices. Okay? So I assume you saw what a matching is before, but maybe you haven't seen it, right? Who has not seen what a matching is? It's okay, don't be shy. It's all right. Have you heard of the word matching? Okay, but formally, what is it in an undirected graph? It's a set of edges. So here is a matching.
So those 3 edges, anything more? You can add this, right? Yeah?
That's one matching, right? Okay. So, and you want to find a maximum matching, right? A set of edges which is a matching, and the size is the matching is how many edges there are. Okay. All right. So it's a very simple problem. This is called the Peterson graph, by the way. It's a very important graph in graph theory. Okay. Okay. So that's so what I drew. How many edges are there in that? 4, right? But you can do better. Okay, 5. You want to find that one. Okay. Okay. But we'll see. We'll first study bipartite graph matchings, and then we'll come to non-bipartite graph matchings because they're more difficult in a few lectures' time. Okay. So, what is a bipartite graph? A bipartite graph is a graph which has 2 sides, and all the edges are going from one side to the other side. Right? Bipartite, 2 partitions. Right. Okay. Now, so a bipartite graph has 2 sides usually, L and R, left and right, or U and V, you know, V1, V2, many ways of defining it. So you want to find a maximum matching in bipartite graphs, and this has a lot of applications. And why is that? So because it models resource allocation very, very simply, right? You know, so think of these as some kind of things like jobs, and these are machines or people, right? Right? And what does these edges represent? These edges represent the fact that this job can be done by that person. Okay? That's the thing is, can this job be assigned to that person? Right? So if they can, you put an edge. If you cannot, you don't put an edge. Okay? Now, so that's a very common situation, right? Allocating things to people or jobs to machines, that's a very common activity, right? Ads to slots, right? You know, and many such things are naturally modeling things that come up in our practice, right? That you know, boys to girls, hospitals to residents, you know, there's things called stable matchings, and right, you know, many resource allocation problems can be modeled this way. And now the question is, you know, what is a matching in this bipartite graph? What does it mean, right? It means that, you know, we want to assign a matching in the bipartite graph corresponds to a set of edges, right? So what does it mean? It means that, you know, only one edge is incident to any vertex, right? That means we want to assign this, an edge corresponds to assigning this job to this person, okay? And this job to this person, it says basically that you can assign the job to only one person, and no person can get more than one job. Right? If you have a bipartite graph, the matching means that, right? This is an assignment of jobs to people such that each job is assigned at most to one, each job is assigned only one person, not to 2 people, and no person gets more than one job. Okay? Now we'll see more complicated things where person can get multiple jobs and things like that later on, but this is simplest setting, right? Okay? Okay, so that is what it means, right? So in this case, you know, this graph, this is a matching of size 3, and you can do better, and this is a matching of size 4. Okay? Okay? So what you want to do is that you want to compute, given a bipartite graph, the matching of largest size. Okay? That makes sense? Okay? Ideally, maybe you want to say, you know, does this graph have a perfect matching? What does it mean, a perfect matching? That means every job is assigned to some person, right? Right? That would make sense. Perfect matching is that every vertex is matched, right? Ideally, I mean, maybe a more interesting application is, can I assign all these people to, all these jobs to these people with the condition that every job is assigned to a person, exactly one person, because I want to give that job, and no person gets more than one job, right? That would be a perfect matching. But for that, first you have to have the same number of jobs and people, right? Okay. But maybe the edges are representing assignment restrictions. Which person can do which job, and it is a complicated problem, right? You know, you can't tell easily. If there are many edges, many 100 jobs and 100 people, and you have a complicated graph which tells you which person can do which job, it's not obvious at all how to check whether all the jobs can be assigned to all the people respecting these conditions, right? But there's a very simple reduction to compute the maximum matching in a bipartite graph using network flow. And the thing is extremely simple. Okay? So you want to compute a maximum matching in this graph, you just add one super source and one super sink. Okay? You put one source, one sink, right? Connect the source to all the left vertices by directed edge. Make all the edges directed from left to right. Connect all the right vertices to this sink with one edge, directed edge. Okay? And all capacities are 1. Okay? Unit capacity graph. My claim is you compute the maximum flow in this graph, that will give you the maximum matching in the original bipartite graph. Okay? Okay? Do you see it intuitively? Or, I mean, just, does it make sense? Yeah? Okay, let's see why it's correct. Yeah?
I thought it was trying to find the maximum node before.
Oh, yeah, that's one way of thinking about it, right? Okay, in what graph though? Okay, so there are two ways of thinking about that. One way is that you could make, in fact, you can make the graph undirected. You put S here, T here, but make the graph undirected, and then ask for the maximum number of node disjoint paths between S and T. Okay? But that also works, but then you have to convert that into a directed graph and then do all that stuff. You might as well do it directly using a directed graph. Okay? It is true, it has a node disjoint aspect of it, but you can easily model it directly using edge-disjoint paths and capacities by the way we construct it, because it is so simple. So it's easier to do it this way than go through that. But it's good conceptually to understand that also. Okay? Okay? So, so everybody sees a reduction. I mean, the picture is clear, right? I don't have to describe it in a detailed fashion. Now you put all capacity 1, you compute the flow. And then I claim that, it gives you a number, right? What does it give? It gives you an integer because all the edge capacities are things. I claim that is the size of the matching, maximum matching in this graph. Okay? Now I have to convince you that it's correct. Okay? Well, part of the reason to convince you is to teach you that when you do a reduction like this, you have to go through a proof to make sure that even though it looks intuitive that you are doing the right thing. Okay? So what do I need to convince you? How do I prove that this reduction is correct? Formally, what do you need to write down even to say, how do I prove it? You have to prove that the original graph G has a matching of size K if and only if G prime, the new graph we get, has a maximum flow between S and T of value K. Okay? That's how you even want to formalize it, right? That G has a matching of size K if and only if G prime has a flow of value K. Okay? All right? It's, it's useful to think about what does it mean, how do I write down even a statement which would imply what I want, right? If the reduction is correct is the most basic thing you want to write, right? But that's not enough, right? What does it mean to specify that the reduction is correct? So, okay, let's do the two directions. If there is a matching of size K in the original graph G, I want to claim that there is a flow of value at least K in this G prime. How do you do that? Okay, so capacity of region, okay. So, okay, that's what we want to say. If G has a matching of size K, then G prime has a flow of value K. Right, okay, I mean so typically when you want to prove this, remember this statement has only numbers in it, right, K and K. But to prove this, you need to actually work with the structure, right, okay, then you say, okay, let M be a matching of size K in G. You would actually construct the flow for me, right, okay. So what does it mean that there is a matching of size K in this graph? What is a matching, right, that means that there are many edges, but I can, this is a matching, I don't know, maybe, this is a matching, right, all right? Okay, there are other edges too, right, which I am not drawing, right. From this, you have to convince me that there is a flow in G prime that we construct which of value k, right. Okay, I claim that you can do this, right, so you say, okay, I'll remember in the new other graph, okay, so let me draw it again, if I can. Okay, all right. I've forgotten how to draw this. Okay, okay. Let me just do it. Okay, so the okay, so that is G, right? Okay, and okay, so this is G and this is G prime, right? G prime has what? It has this super source S and super sink T, and it has all these arcs, right? Agreed? Okay, so we say, okay, we put 1, 1, 1, 1, 1, 1, okay, sorry, 1, 1, okay. So we are going to construct a flow of value k in this G prime by saying put 1 on all those matching edges. Remember, the edges are also directed now, right? These edges are what nonsense. Okay. Okay. These edges are now directed in G prime. I'm going to put flow of value 1 on each of those, and 1 on all the arcs coming from source to the left endpoint of the matching edge for each of those matching edges, and 1 on the right, the edge going from the right endpoint of that matching edge to the sink, and 0 on all the other edges. Okay. Now, first you have to check, it's laborious, but it's not hard to see. First you have to check that it's a valid flow assignment, right? Yeah? That means, you have to check conservation, capacity. Capacity constraints are easy because all the capacities are 1, right? I put our zeros are 1, so it can't violate capacity. Why is flow conserved? Because, then that's where you have to use the fact that it's a matching, right? That I'm putting 1 here, but there's only one edge going out of that vertex. Otherwise, I won't get flow conservation, right? Okay? Okay, so flow is conserved because of the property that the edges form a matching. Otherwise, it's not. We won't have it, right? We're using the fact that these edges form a matching in arguing that this is a valid flow. Okay. Now we have to check that the value of the flow. This is a valid flow, and once here's a valid flow, what is the value of the flow? It's a flow leaving the source, and it is k units because we put k edges going out. Okay, it's not hard to see, but you see. So we're creating a flow of value k in the graph. So the picture tells you everything, right, more or less, right? But you have to kind of go through it, okay? Okay, so if you have a flow of value k, sorry, if there's a matching of size k, there is a flow of value k. It's easy to see. Equivalently, there are k edge-disjoint paths between S and T, right? Each is. Okay. Now, what about the other direction? Okay. The other direction is that you need to argue that the other direction is that there is a if there's a flow of value k, then if G prime has a flow of value k, then there's a matching of size k. Why is that? Okay, now this is more or less basically saying it's an integer flow. Okay, and we can compute k edge-disjoint paths between S and T, right? Because it's unit capacity graph. Okay, Now, let's look at those paths. Because it's a layered graph, all the edge disjoint paths have to start at S, go to the first layer, go to the second layer, and go to the third layer. Okay? Okay? They also have to be node disjoint. Why should they also be node disjoint? I mean, I'm giving you a sort of informal proof, right? Why? They should be node disjoint, internal node disjoint because of the capacities, right? S to a vertex on the left side has capacity 1. Okay? So if they're edge disjoint, they also have to be node disjoint. Because there's only one edge going into each vertex on the left. Okay? All right? So basically, I mean, you can go through the proof. If you do a flow decomposition on the flow of value k, you get k paths. Okay? Now, each of those k paths has length 3, right? It starts at S, goes to a vertex, goes across, goes to T, right? Now, look at all the edges used in the middle. You have to convince yourself or argue formally that they form a matching, right? There are many ways of doing it. It's laborious, but it's not hard. Okay? You see the picture, you get the idea, right? Everybody understands the intuition for it, or should I go through it more carefully? Yeah? Okay, the only thing you have to realize is that to make the reduction, to prove the reduction, you have to basically give me the matching from the solution. Without that, you can't argue the correctness. Okay? So how do you construct the matching? You look at all the edges with flow equal to 1 on the original edges between L and R, and then those are the edges of your matching. Okay? That's important. Okay? The rest is maybe detail, but you cannot prove things with reductions unless you convert a solution for the problem to the solution to the original problem. Okay? All right? Okay. All right. So I don't want to spend more time on that. So you can look at the notes to see the correctness of the reduction. Now the question is, what is the running time of this algorithm, right? Well, we have a graph of original graphs. Whenever you do reductions, what happens is that you take the original instance and you do something and you create a new instance and then you run an algorithm on that. Okay, so when you want to express the running time of the algorithm, you have to use if you wrap it around, then you start with an instance and you output a solution, right? You have to think about what is the size of the starting instance. You transform it into a new instance which may increase its size, and then you run some algorithm on that. You have to express the final running time as a function of the original input's size. That's important, right? If you take a problem and blow it up into exponential size and run a polynomial time algorithm on that, it's still exponential in the original input size. So you're not getting a polynomial time algorithm, right? So you have to worry, when you do reductions, you have to worry about what happens to the size of the problem when I go from this original problem to a new problem. Okay, in this case, what happened? We took a graph with m edges and n vertices. Did we increase the size too much? Not much, right? How many vertices are there in the new graph? If the n was the original number of vertices, how many vertices are there in the new graph? N plus 2, right? So not bad. How many edges did we add? We added 2n edges, right? Or no, n edges, right? Because if n is the total number of vertices, we add 1 edge for each, right? So the number of edges in the new graph is only, if m was the number of edges in the old graph, the new graph has m plus n edges, right? Okay, and n plus 2 vertices. So it's a very simple reduction. We didn't increase the size too much, right? So m and n are comparable, right? And then what do? We run Ford Fulkerson. What algorithm should we run? We can run any algorithm. I mean, you have to decide which algorithm you want to use, right? You can say, I'm going to use a complicated mn time algorithm because I just want to think about it that way, right? But in this case, you realize that this is a unit capacity graph, and the maximum value of the flow is what? Only n, right? Because the matching size can at most be n, right? There's a min cut around s of size n, right? So even if you run Ford Fulkerson, which is the simplest algorithm, you will get mn time, right? Because even if you are not clever, you will terminate in mn time, okay? In particular, if the flow value is very small, if you suspect that the matching size is very small, in fact, it will terminate even faster. Okay? Because it's a unit capacity graph. Okay? So that's what you need to say, right? In fact, the best known, no, in fact, that's not, this is old, but you can get m square root n, and right now the fastest running time is m to the 11 over 10 over 7. Okay? So there are many, this is not a, it's a very interesting problem. Okay. Now we are going to talk about perfect matchings, right? So perfect matching is a matching which matches every vertex, right? That's why they're called perfect, right? Okay. Now one interesting question is, can we check whether a graph has a perfect matching, a bipartite graph? We can, right? Because we are finding the maximum matching, right? So you check, is there a matching of size n where n is, n over 2 where n is a number of vertices, right? Then it's a perfect matching, right? All right, so we know we can compute the maximum matching size, so we can check if the graph has a perfect matching, okay? But we are interested many times in not just knowing whether the graph has a perfect matching, but combinatorially, when does the graph have a perfect matching? Okay, because there are many situations where you want to claim that there's a perfect matching without knowing the graph explicitly. Okay, so we'll see why that is useful. Does this graph have a perfect matching? Why not? Okay, suppose I give you this graph, and let's say you want to convince your friend who doesn't know anything about computer science, but matchings are easy to tell people, right? Everybody understands the matchings, right? So you say, here is a graph, and you say, you claim that there's no perfect matching in this graph, right? And your friend says, no, I think there's a perfect matching. How can you convince the person? You can say, okay, look, I know maximum flow. I can run the algorithm and convince you that, the algorithm is telling me that there is no perfect matching because the maximum matching size in this graph is 4, okay? I'll say, come on, right? You tell me, so that means you have to convince your friend about the correctness of flow and correctness of the reduction and, okay. Is there an easy way to convince your friend that there is no perfect matching? Two nodes on the right hand side. Which two nodes? This one? Yeah, third and fourth. What about them? This one? Yeah. Okay, yeah, okay, so you're saying, look, this guy has to be assigned to this guy, and then this guy has nobody, right? Yeah, that's one way to so okay, now, okay, if it gets more complicated, how do we know, right? Okay, so that's that's a good question, right? That's an easy proof to convince your friend that, okay, they'll be convinced by this argument that, right? Now the question is, can you always convince your friend by an easy proof? Right? Okay, and in fact, it turns out that, okay, one way, when is it not feasible to find a perfect matching? If the number of left-hand side vertices is not equal to the right-hand side vertices, clearly you can't have a perfect match, right? So let's assume that's an easy case, right? Okay, so we'll assume that left-hand side is equal to the right-hand side. Okay, the question is there anything which is necessary and sufficient that's easy to give you that condition? And there is. Here is one necessary condition. When is it, why is it necessary? What is the condition that is necessary, right? Suppose, I have this big graph, L, and here is R, okay. And I find, some set of vertices, there are many vertices here, and then this is X, okay, all right? I look at the neighborhood of X. What is the neighborhood of X? All the guys on the right-hand side which have an edge to from this guy. Okay? So that means, I look at everybody that they have edges to. Okay? Okay? Okay, this is the neighborhood of X.
Okay, this, let's call this n of x.
Okay, is n of x clear? What is n of x? It is the set of all neighbors of x. That means there is nobody outside n of x who has an edge to x. Okay? Agreed? Notation clear? Okay, to have a perfect matching, I claim that the neighborhood of x should be at least the size of x. Yeah? If there are fewer neighbors than x, suppose there are 10 guys in x and they only see 3 guys on the right hand side. I cannot match x to anybody other than my neighborhood of x, right? Yeah? I can only match x to the neighborhood of x. If the size of the neighborhood of x is smaller than the size of x, then there is no way there is a perfect matching. Is that clear? Yeah? Okay. So if you find a set of vertices like this, x, such that neighborhood of x is smaller than the size of x, you can convince your friend, no? Yeah? Agreed? So how can you have a perfect matching? These guys cannot be matched because there are too few people to match them. That's an easy certificate, right, to convince your friend. Yeah? Is that clear? Okay. So now the question is, if there is no perfect matching, can you always show such a simple certificate? Or conversely, if it is true that for every subset of vertices x on the left hand side, the neighborhood of x is actually bigger or at least as big as x, is it true that the graph has a perfect matching? Okay, it's the same question. The question is, if the graph has no perfect matching, can you show a set x which fails this test? Okay? Or equivalently, if every set does not fail this test, then is it true that the graph has a perfect matching? They are the same question, right? Okay, you may not be easily able to find such a set, right? But does there always exist such a simple way of convincing somebody that a graph doesn't have a perfect matching? Is it clear what I'm saying? Yeah? Okay, at least it is a necessary condition, right? If a graph has a perfect matching, then for every set x on the left hand side, the neighborhood size should be like that, right? Is it sufficient? If for every set x, then, okay? And the answer is Hall's theorem. It is true that if for every x on the left hand side, the neighborhood of x is at least as large as x, then the graph does have a perfect matching. Okay? It doesn't tell you anything about the algorithm, right? It just simply says that it's a necessary and sufficient condition for the existence of a perfect matching. Okay? All right? Is the theorem make sense? Yeah? Right? Okay. One direction is a necessary condition, right? If we see it's a necessary, we have to prove that if it is true for all sets x, then it is sufficient. Okay? So why is this interesting theorem, right? Here is a nice fact. You can prove it in many ways. Suppose I give you a regular graph. What is a regular graph? A graph where every vertex has the same degree. Okay, if I give you a bipartite regular graph, it always has a perfect matching. It's not obvious at all, right? So if everybody has exactly the same number of the same degree, then I claim it has a perfect matching. Only in bipartite graphs. It's not true in non-bipartite graphs. Okay, is it obvious at all? No, right? Wait a second. I don't know anything about how to convince myself there's a perfect matching, right? We have an algorithm, but it doesn't tell us. I'm not even telling you the graph, right? I'm simply saying the graph satisfies a simple property that every vertex has the same degree, and then automatically I'm able to tell you that it has a perfect matching, right? Without knowing anything about the graph, right? Why does this theorem tell me that the graph has a perfect matching if it is regular? Let's verify that it satisfies the necessary and sufficient condition. Okay? Okay, if the graph doesn't have a perfect matching, this theorem says there must be an x, okay, and in the neighborhood of x is smaller than x, right? So maybe I should draw it the other way around, right? That the neighborhood x is looking like this, right? Okay, is it possible in a regular graph?
Okay, I claim it's not possible in a regular graph. Why? Because let's look at the counting argument, right? How many edges have to go out of X if it is, say, D regular? There are X times D edges going out, right? And because bipartite, all the edges have to go to the right-hand side. Okay. What happens on the right-hand side? How many edges can come into the neighborhood of X? Exactly D times the neighborhood of X, right? Because they're all degree D, right? So let's call this Y, then I get, Y times D is an upper bound on the number of edges. Okay, but if Y size is less than X, then how is that possible? Right? Yeah? If Y is smaller than X, Y times D is smaller than X times D, right? Okay? But then that means that, we violate the degree condition here. Okay? Okay, X times D edges are going into this, and Y is smaller than X, that means that somebody should have degree more than D here. But it's a D-regular graph. Right? So in a D-regular graph, you cannot find such a certificate, which means that the graph should have a perfect matching. Right? So you see the power of the theorem, without knowing anything about the actual graph, we can guarantee that any D-regular graph has a perfect matching. Okay? That's the importance of this theorem, right? Because there are many implicit graphs where you want to convince yourself there is a perfect matching, you can use this theorem. Okay? Okay, you should suspect that, it's same as Maxwell-Minkert theorem, right? Basically, in Maxwell-Minkert is also a similar theorem that if you want to convince somebody that the flow is not large, how will you convince them? You don't have to give an algorithm, you can give the cut. A cut is a compact certificate to convince somebody that the flow is not too large. Right? And we know it's an exact certificate, right? So the same thing. So we can prove the Maxwell-Minkert theorem, this Hall's theorem, using Maxwell-Minkert theorem. Okay? Okay? Why is that intuitive, right? Because see, look at it this way. When does a graph have a perfect matching? It means that in the reduction we did, the flow has to be a value what? The size of the left-hand side, which should be equal to the size on the right-hand side, right? That's when we know that there is a perfect matching in the graph, right? Agreed? Okay. But we know the value of the flow is equal to the value of the min cut. So if there is no perfect matching, what do we get? We know that there is a min cut of value less than half the number of vertices. Okay? Now, using that min cut, we are going to argue that we can find a set which violates the Hall's condition. Okay? Okay? Remember, we don't know the graph exactly, but we see that's the important thing of this theorem is that we don't know exactly the graph. It only satisfies some condition, and we still want to argue it has a perfect matching, right? So it is not intuitive how to do that, right? You can do it by induction, you can do other ways, but this is one way of doing it. Okay? If the graph doesn't have a perfect matching, in the reduction, we create this directed graph. In that, the flow must be strictly less than n over 2, which means that the min cut must be less than n over 2, and we'll use the min cut to find a set which violates the Hall's condition. Okay? Is that clear, the proof methodology we're going to use? Okay? So this is a purely combinatorial statement. It is not an algorithmic statement, but we're using the algorithmic properties of flow and Maxwell-Minkert theorem to prove a combinatorial statement. Okay? All right? So again, coming back to your friend, you can use the algorithm, okay? And you know whether the graph has a perfect matching or not. If it doesn't, you get a certificate which you can show to your friend. You don't have to tell them to convince them of the algorithm. The algorithm at the end will give you a min cut, which gives you a set with the property that the neighborhood is small, and you can show them the set and say, look, this set of vertices have few two neighbors, so there is no perfect matching. It's easy to convince them without actually making them convinced about the algorithm. You can use the algorithm to produce the set though. Okay? Does it make sense? Okay. All right. Let's see how to prove this, right? It's easiest to do, okay. Okay, here is what I want to prove. If for every set x on the left hand side, the size of the neighborhood is greater than or equal to the size of x, then I want to show you that the minimum ST cut in the graph G prime that we created is of at least size n. Here n is the size of the left hand side, which is the same as the right hand side. If the left hand side is bigger than the right hand side, already we have a contradiction, right? Yeah? Okay. So in fact, I'm going to prove a slightly stronger theorem that I don't care about the right hand side. When I think of a perfect matching, I want to match everybody on the left hand side. The right hand side could be bigger. Okay. All right, slightly generalization, right? I want to match everybody on the left hand side. So the right hand side is at least size n, and the left hand side is n. Okay? Okay? Okay. So proof by contradiction, right? Here is I don't know if I have a picture. Okay. Okay. So maybe I'll draw it for you. It's easier to draw it. Okay. So this is L, this is R. Okay. I don't know this graph. That's the problem in this proof, right? I mean, I have to prove it in a generic way. Okay. Okay. I want to prove that the ST min cut is at least capacity of n. Okay. Okay. So take any cut from S to T in this G prime. How does it look like? How does an ST cut in this graph look like? It has S in it, some parts of L and some parts of R, right? But not T. Okay. So the cut will look like this. How will it look like? Okay. Any cut which is separating S from T will look like this, right? I'm going to draw it pictorially for simplicity like this, right? This is A, right? A contains S, but not T, right? Okay. Okay. So and the rest is B, right? Okay. Okay. So okay. So let's look at this set of vertices. Call that X. Okay. And then we'll call this set of vertices Y. Okay. Okay, what is the capacity of the cut though? Let's count the capacity of the cut. What is the capacity of the cut? How many edges are leaving this cut? One edge from S to all these vertices, right? The capacity of this cut is what? Is greater than L minus X, right? Yeah? L minus X plus what? Everybody from here to T, right? Yeah? No, is that a cut? No, right? These guys, right? Okay, plus Y, okay? Plus what? Edges going from here to here, right? Okay, we don't know that, right? That's the hard part, right? Okay, so what is the capacity of this cut? It is L minus X plus Y plus, I mean, it's equal to, plus, so I'll claim, I mean, I'll write the notation like this, EX R minus Y. Okay, what is EX R minus Y? The set of edges going from X to this side. Okay, all right. If I can prove that this, for any cut, this is bigger than size of n, then I'm done, right? Because that's what I want to prove, that every cut has capacity at least size n. So I picked an arbitrary cut, so if it is bigger than n, min cut also should be bigger than n. Is that clear? Yeah? Okay. The problem is, how to bound this, right? Okay? Okay, so let me do it this way, like we did the thing, right? Okay, so I don't know this, right? How many edges are there from this side to this side? Okay, going back to my cartoon picture, right? Okay, look at this set X, right? Okay, from this condition, how many neighbors does this set X have? At least size of X, right? Okay, agreed? Okay, where are those neighbors? I don't know, right? Some of them could be here, some of them could be here, right? Okay, okay, maybe all of them are here, and then in which case I don't have any, okay? But I can assume the following, the size, if this X has n of x neighbors and the size of n of x is at least x, okay? How many neighbors should be outside of y? I can subtract y from that, right? Maybe y is bigger than n of x, in which case I'll even get negative numbers. But I claim there are at least n of x minus y neighbors of x here. Yeah? Does it make sense? This guy has n of x neighbors. How many are outside of y? At least n of x minus y, right? Okay? And each of them must get an edge from x. What does it mean to be a neighbor of x? That they have at least one edge coming from x, right? So can I bound this by n of x minus y? Yeah? I can say that this is at least n of x minus y. Okay? Agreed? Is that clear? Okay, I don't know how many the edges are there, but I claim I can take this and say it is greater than n of x minus y. Right? Agreed? Is that clear? Okay. Okay, now, so that min cut, now it's instead of equality, I'm going to put greater than equal to, because I don't have equality anymore, I'm just lower bounding it. Okay? So what is this now? It is L minus x plus y plus n of x minus y at least. So y and y will cancel. Okay. What do we get? It gets L minus x plus n of x. Okay, but we have the condition that n of x is greater than or equal to x. So this is at least L. Okay. So I took an arbitrary cut and I argued for you that the capacity of the cut is at least L. So the min cut also must have capacity at least L, which means that the max flow is at least L, which means that there is a flow of value L from S to T, which means the matching size is L. Yes? Okay? So it's basically max flow min cut theorem is giving us Hall's theorem basically. Questions? Okay? All right? Yeah? You don't need, Hall's theorem is typically proved in books on matching theory or combinatorics if you just don't, without algorithms, right? You can prove it by many induction things and stuff. Implicitly, it's a reduction to max flow min cut. This is one proof. Okay? All right. Okay. So that's the proof, nicer pictures if you want, and you can do the algebra and okay? Okay? We'll see more applications of assignment problems and stuff and things like that next week. I'm going slower than I thought, but it's fine. Okay? Okay. Good.
For the previous slide, I
Ah.
have the question.
Okay.
And
Okay.
it's the picture you just drawn.
Okay. 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 Yeah. What is it? Yeah.
Yeah, so here the first part is L minus X. That means maybe
Yeah.
how many nodes
Yeah.
here, right?
Yeah.
And this one is how many edges?
No. Why is this part?
Yeah, why is this part?
Yeah, and this is, yeah. How many edges are going across?
Across here.
Mm-hmm.
So maybe here, some nodes here, and also share the nodes.
That's
as
okay, but the
this.
capacity of the cut is defined as how many edges are going, right? How many edges are leaving this side.
Oh,
Don't worry about what it is. We are now in a directed graph. We don't care about nodes and edges. I mean, it's just how many edges are going from outside this set.
okay.
Yeah, sure, yeah, they can.
Oh, we just only care about the edges.
Yes, yeah,
Oh,
yeah. Yeah, that's good, right? We don't worry about nodes anymore.